So now the analysis becomes more or less a mathematics problem. Let's try to minimize this function. We know how to do that. We set 0 equal to the derivative of the quantity we are minimizing, which is this average energy, with respect to the variable that we're minimizing it with, and that's delta R. I then take this derivative. The first term then is going to give me, well, 1 over delta R squared brings out a factor of -2. I then have my constants involved, which were h bar squared over 2m. That's nice. I can see the 2's will cancel. And then 1 over delta R squared picks up another exponent, so it's 1 over delta R cubed. The next term was minus Coulomb's constant times the square of the electron charge. And then the derivative of 1 over delta R gives me a minus sign. And then again, I go to the next exponent, so that's delta R squared. And then the sum of these two terms has to be 0, as we said, at the optimum. Now, we know how to solve an equation like this. Okay, sure, we can cancel out the 2's. The other thing we know we are going to do is we're going to take this negative term, right? We're going to move it to the other side of the equation. And then we're going to notice, oh, we've got this delta R cubed on the bottom, which we really don't like. So we'll multiply both sides by that delta R cubed, which will cancel it from this side and then move it to the top on the other side. So you can see I'll have delta R cubed over delta R squared. So on the left side of the equation here, I will just have delta R equals. And then to finally solve it, I divide both sides by Coulomb's constant E squared. So I'm left with what was on this other side of my equation was h bar squared over m. But now, in order to solve for delta R, as we've said, we also have to divide by Coulomb's constant times the square of the electron charge. And that gives me the size of my atom. And the beauty of this is that if you think about what we've just done to get to this point, we began just like Empedocles would want us to do, right? We began here with just basic facts of nature, the nature of our two constituents, right? Their interaction, and some knowledge about based on previous empirical observations about how such entities behaved, which we've boiled down to our Heisenberg uncertainty principle, and then just with the power of the human mind and the aid of a pencil, right, and a screen to write on, without anything else but our minds, we've been able to carry through this derivation and get a beautiful, at least order of magnitude estimate for the size of the atom. And this is really amazing and useful, right? Because once you know the size of the atom, you know how many atoms there are in a crystal. That then tells you Avogadro's number. All of these things are coming just from the basic constituents of nature and just a few values of fundamental constants. It's really amazing. We've actually, after 2,500 years, we're fulfilling finally Empedocles' dream. Now, it's true, so far this is only an order of magnitude estimate, but nonetheless, just even to get the size of the atom to an order of magnitude is a remarkable accomplishment. So let's see how well we did on this. Let's put in the numerical values. Now, in order to do that, let's see. Well, h bar, we've learned, is very close to 10 to the minus 34th joule seconds. The prefactor on it, you might recall, is just about 1.05. It's pretty close to just 1. That's going to be squared in my numerator. For my denominator, I have the electron mass. The electron mass, you'll recall, is almost exactly 10 to the minus 30 kilograms. It does have a prefactor on it, which is 0.911, but again, that's pretty close. Mass. Coulomb's constant. Now, you may recall it's something like 8.99 or 8.95, very close to at least 2 decimal places to 9 times 10 to the 9th. Now, that's very close, in fact, to 10 to the 10th. It's actually 0.9 times 10 to the 10th is Coulomb's constant, and the units on it are joule meters per Coulomb squared. And finally, we have to multiply by the square of the electron charge. The electron charge from milliken was 1.602 actually, but 1.60 if we just want to go to 3 decimal places, which is where all of these are, times 10 to the minus 19th coulombs quantity squared, like so. Okay. Now, I know we're really dragging things out here, but it's useful, really, I think, to go through this exercise. It's kind of fun, right? Because these are all things that we can carry around in our human minds, and we want to see really how well we can do, say, without the aid of a calculator or the internet or Wolfram. Can we just do it ourselves, like we were stuck on a deserted island somewhere, didn't have a calculator or anything, but maybe we have our fingers and sand that we can draw in, and we suddenly have an urgent need to know the size of the atom. Well, here's how we could do it. Okay, so let's first check our units. Notice on top I've got joules squared, but I've got joules on the bottom, so I can take care of all my joules by just having 1 power of joules on the top. I've got seconds here that have to be seconds squared. In the denominator, we have kilograms from this term. We have, oh, it's nice, the coulombs squareds cancel. I already took care of my joules. I took care of my kilograms. The only thing I didn't take care of was my meters. Now look carefully at this. Remember that the joule itself is a kilogram meters squared per second squared. So then my kilograms cancel, one of my meters cancels, my second squareds canceled, and all I'm left with is meters. So we got the units right. It's going to come out in meters. So let me just put M here for meters for my answer. Now, next, powers of 10. And this is an order of magnitude. So let's see what we do order of magnitude. So follow along with me, because it's kind of fun to get this answer in your head, right? So 10 to the minus 34 squared would be 10 to the minus 68. When I divide that by 10 to the minus 30, that's like multiplying by 10 to the 30. 10 to the minus 68 over 10 to the minus 30 is 10 to the minus 38. Then I divide by another 10 to the 10, so that's 10 to the minus 48. And now I'm dividing by 10 to the minus 19th squared, which is 10 to the minus 38. So 10 to the minus 48, divide by 10 to the minus 38, leaves me just 10 to the minus 10 meters. That's exciting, right? Because that is an angstrom. So we've already got the size of the atom to orders of magnitude. It's exactly about 1 angstrom, or if you want, that's in 0.1 nanometers. So that's pretty cool. The next thing is, while we're at it, let's just practice a little mental math. This is a good skill to have to make slightly better estimates. So now we can take care of all the numerical factors. So 1.05 squared. You might recall, just a little aside here, right? The fact that 1 plus x from your binomial theorem is 1 plus 2x plus, tiny terms, well, there's a tiny term, x squared, but that's pretty tiny. So 1.05 squared, you just double the 0.05. So that's 1.1. Then I have to divide by 0.9. But you will also recall, right, that 1 over 1 minus x is about 1 plus x squared, right? There's a geometric series there, right? So if 0.9 is just 0.1 short of 1, then 1 over 0.9 is going to be 1.1. So I had 1.1 on top, and then I'm multiplying by another 1.1. That's 1.2 so far. Now I have a divide by another 0.9. So again, I multiply by 1.1. Well, 1.2 is what I had so far, times a 1.1. That's like 12 times 11 is 132. So that's 1.3. So I've got 1.3 on top, and then on the bottom part I've got 1.6 squared. Now 1.6, remember, is around 1.4, which happens to be the square root of 2, so this should be about 2. But we can do better, right? Because 16 squared, we should know 16 squared, right? 16 is 2 to the 4. When I square 2 to the 4, that's 2 to the 8th, and that is exactly how many numbers I can represent with 1 byte of information, 2 to the 8th is 256. So the denominator is 256, but that's just the digits. Remember, the value was somewhere near 2. So the answer would be about 2.56. So putting this all together, notice that 1.3 actually times 2 is 2.6, which is basically exactly what I have in my denominator. So I've got basically about 1/2. So it's pretty close actually to 0.5 times 10 to the minus 10th meters. And this is actually exactly the size I had told you all we should use for the electron in the hydrogen atom, about 0.5 angstroms. And in fact, it's true. If you put in more numerical value, if you put in the more accurate numerical values or type this through on your calculator, you will get 0.529, the official value, angstroms. Beautiful. So we just happened to get a little bit lucky on this one, right? Because we were doing order of magnitude estimates. But nonetheless, I want you to know that it is precisely this combination of fundamental constants, without any funny prefactors in front, that actually give you the official size of the hydrogen atom.